experimenting a little bit. Oh, I go to sleep, somebody help wake me up. Oh. Okay. All right, I'd like to welcome you to Astronomy Club of Tulsa. So there's Mike and everybody gets set down. Lauren, you can have a seat up here and I'll get you in a minute.
All right, sorry. Taking care of things.
Time to get going. Did we get our Zoom going yet?
Zoom is up and running.
Okay. Welcome to all of you that are watching us virtually. Some of our members don't live in the Tulsa area, or they're just not able to get out as much. So we're still experimenting with that part of it. But I'm John Land, the president, and there's Skip, he's our secretary. And Don's back in the back, our vice president. We've got some visitors here tonight, and I've already forgot your names. Tell me again. Micah and Nikki? Ricky. Well, I got close. I met somebody else that said they were first time here. So, yes, what's your name?
Megan.
Megan. So glad you're here tonight. And so we're going to have a good program. We got our guest speaker, Lauren Harrington, here. And she's going to tell us about the stars. I'm trying to spotlight out because we have an astronomy convention coming up in June, first week, second weekend of June, 9, 10, and 11. And it's kind of hard up here to see the speaker. Is it? Well, anyway, yeah, I probably don't want to. Anyway, I thought I would experiment with it. But anyway, okay, oh, he's got it up there. So our tonight's program is, somebody just remind me that this is May the 5th, Cinco de Mayo. And I made the schedule back in December, that didn't register with me. So there's lots of other things going on in the community this weekend. All right, next one. So there's some of our events coming up. We have observing night at our observatory. If you haven't been there, it's about 22 miles southwest of here, south of the little town of Mounds, Oklahoma, up on a hilltop. And we have a telescope up there in a dome, and then our members set up telescopes. We've got about an acre of land out there where we set up stuff, a nice parking lot. So we have what we call guest and members nights, where people can bring their guests, or just the general public can come as a guest. And we set up telescopes, and our vice president usually has his camera hooked up to the dome scope so they can see the galaxies and things. And then for our members, we also try to do another night or the next weekend. We do the first one during third quarter moon, and the other one close to new moon. So for the diehards like Brad that want to stay up all night, they don't have to worry about the moon coming up and messing up everything. So you can see the dates up there. May the 12th, coming up Friday, is our guest night. And if we get clouded out and the weather's better on the 13th, we'll try the 13th. And then May the 19th is our members night. And then our convention comes up June 9, 10, and 11. Starts on a Friday here. We'll have a barbecue catered by Oklahoma Joe's Barbecue, and we'll kind of welcome our guests. And then we'll take people out to our observatory, and that's one of the things I need. I need volunteers to help guide the group out there to the observatory, and also a few volunteers just to be out there ahead of time and be set up when the people start arriving. So that's on Friday night after we have our barbecue.
There's been some questions about about the observing out at the observatory during the conference, and it is planned to be one night, Friday night, and then if it's inclement or cloudy, then we'll have it on Saturday night. It's not planned to be both nights. And the volunteers, we're going to, like John said, we're going to need some people to go ahead while the barbecue is still going on and set up their telescopes so that the people can get there and look through the telescopes, and then other people to shepherd them out there.
Thanks, Brad. You changed the schedule. So anyway, there's the information about, it's a mid-states region. It's Oklahoma, northern half of Oklahoma, Kansas, Arkansas, Missouri, and all but the panhandle of Nebraska are in our mid-states region. I've forgotten how many clubs it is. It's over close to 30 clubs that are part of that region. And then, so we have a number of good guest speakers coming on Saturday, and a couple more, or 3 more on Sunday. We've got a couple of good planetarium shows. Dan Zielinski, our planetarium host, is going to share one of the shows that his students have put together. Each year they put together excellent planetarium shows. And Byron Labadie, there he is in the back, got a chance to go to Chile, however they say that, I always say it wrong, to see some of the big telescopes that are down there in the southern hemisphere. He went down there in the summer, in the middle of December, in the southern hemisphere. So he's going to tell us a little bit about that. And then they have an excellent program that they produced, All Sky Planetarium program. And so we have some other guest speakers. One of the speakers is our own member who works with asteroid occultations, a gentleman from the Bartlesville Club. They have been working with getting the Osage Hills State Park designated as a dark sky site. And our keynote banquet speaker, that's on Saturday night, is coming to us from the University of Arkansas, and he's going to talk about Einstein and gravitational waves and this new frontier of a way to observe the universe. So his name is Daniel Kinnifick, if I can say it right. But anyway, so he's coming. Also, we're going to have the Broken Arrow Sidewalk Astronomers, along with a group called Science Heads out of California, put together a mobile observatory. And it's going to be here in lunch period on Saturday. And they've already kind of had a dry run of it. It's not completed, but they did take it out for a little public event this last weekend, which was well received. All right, next one. So there's a list of volunteers. We're not going to let you out the door till you volunteer. No, but we need a lot of help. We've got 9 people, well, 10 people who've been working since December on the planning team, but we cannot run this convention for 80 to 100 people. There's lots of things to do. So on Friday, we need people who volunteer to come up as early as 1 o'clock, get everything set up. The registration opens at 3 as our guests start arriving. We'll need to set up some tables for the barbecue. Just lots of things to get ready. One of our board members, Kathy Grounds, has put together some decorating ideas for the barbecue banquet. We'll need some people to just kind of help serve at the banquet, like we've done at our club dinners in the past. And then, of course, we'll have to clean up a little bit while most of you go back out to the observatory. Early Saturday morning and Sunday morning, we have a little oh, it's not really a breakfast, but some juices and coffee, some fruit dishes, just for people to come in and kind of get a little refreshment. But that's got to be set up on Sunday morning. At noon, we have our group picture. After the presentation, I'm in need of a volunteer with a good photography skill. We're gonna take it downstairs in front of that Fibonacci symbol. And then we'll have our lunch, wander out and look at the mobile observatory, and we have to move some tables. So I'll explain that later. And then on Sunday, again, we have to set up for the welcome and the breakfast snack on Sunday after we get done here around noon. We'll have to clean everything up so Dan can go home and get a nap. So, there's lots of things, you don't have to volunteer for all, but there's lots of things to be done. So you contact me, you can contact any of the board members. We appreciate your help. All right,
There's a
next.
sign up out front.
Oh, what'd you say, Don?
There's a sign up for volunteers that it's on the table.
Oh, Don says there's a sign-up list for volunteers. Most of you are familiar with the fact that as we came in, that the club is, we've got 2 eclipses coming up, most of you know that. One of them's on a Saturday, October 14th. It'll be over 70% here. It's an annular eclipse where the moon's not quite big enough to cover up the sun, and it's a diagonal path up across southwest Texas and New Mexico and that direction. But it'll be pretty good here. And it's on a Saturday, so we're hoping to have at least 2 events for the public with our club, and maybe probably the Sidewalk Astronomers will have a 3rd location. But we're selling these little packets, there's 5 of them each in the packet with a little bit of information. And I've had good success with this. My daughter teaches 3rd grade, or did at one of the schools. And then I took my family, that's the people hiding behind the paper plates, up to see the total eclipse in Nebraska. Well, I found that these are much more sturdy than the glasses, the eclipse glasses. And I wear glasses, as many of us do. And getting those little paper glasses to fit inside my glasses, it just doesn't work. So for younger kids and those of us that have glasses, what we did, just cut a little hole in not a thin paper plate, but those cardboard paper plates. And you hold it up over your face and look at the eclipse, and you don't come out looking like a raccoon with a sunburned face afterwards. So anyway, we're selling these $5 a kit. And Debbie over here, Debbie and Steve are doing that. Okay. That's probably not, I don't know, that's not mine. Not get it. All right, next up. Oh, a guest presenter in person. So this is Lauren Harrington. She is an astronomer from the Grand Lake of the Cherokees. She works with the American Association of Variable Star Observers. Did I get it right? And she works with their spectral division, of which she's going to excite us with her skills there. She also works with a professor from MIT who works on exoplanets. Is that right?
That's right.
And this summer, you get to go to North Carolina. I cannot pronounce the name of the place you're going. So that's
The Pisgah Astronomical Research Institute.
okay. I am going to get out of the way. That's you. Joe.
Thank you very much. I have to say, you guys have the coolest meeting space I have ever seen. Seriously, this is awesome.
Thank you.
You are going to have to forgive me though for the next training I'm going to be doing, because while I have practiced this talk a lot, I'm not that good. All right, So today we're going to be talking about two of the coolest things in astronomy. That's spectroscopy and stars. Combine the two and you get what I am lucky enough to work on every day. So let's go ahead and start with an overview of spectroscopy. Specifically, what exactly do I mean when I talk about a spectrum? Because I'm going to be doing that a lot in this talk. So this is a spectrum. And if you want to pull up the video version of that.
Yep.
Cool, let's give it just a second. So what this is right here, and you'll see when it starts playing, is a spectrum as seen through my telescope. Got a little diffraction grating that I put on my telescope. It's got a monochrome camera, but I'm showing you this because it's actually pretty common in astronomy for us to take pictures of rainbows, such as that one, with a black and white camera. Makes it boring, but it's more sensitive when it comes to science and collecting scientific data, so that's what we do. When you see something that looks like that, that's a spectrum. That's one version of it anyway. All right, so now let's take a look at another version of a spectrum. So this right here is what I see when I just use my backyard telescope, right? But if I do a long exposure, and I put the color back into it, that's probably what you're more familiar with if you've ever seen a picture of a spectrum before. So that right there is the spectrum of the star Betelgeuse, which if it's not your favorite star, it should be. And basically what you're seeing is the rainbow created by the diffraction grating in just the same way as a prism makes a rainbow. That's what diffraction gratings do too. We use them because they're a little easier to make scientific data with, but same difference. You could use a prism if you wanted. And the darker areas are places where molecules and atoms are absorbing light. They're blocking some of the light that would have otherwise shined at Earth. The lighter areas are where these molecules are not doing that. And so by looking at which patterns show up, we can figure out which molecules are in the spectrum and therefore in the star. You'll see some more examples of that shortly. If you want to do science with a spectrum, this sort of image is very pretty, but it's not super easy to quantify. So there's one other form of spectrum. You're going to see this one in the talk a lot, and that is the graph format. So this is the exact same kind of data, not the exact same star, but the same kind of data. And what I've done here is I've just converted the brightness into height on the graph. So I was able to turn that image into a graph, which can be easily quantified, and we can go do scientific measurements on it and write papers and all that stuff. But it's the same kind of data. All three of these images, which I've shown you, same kind of data, all of those are spectra. Okay. Right. So there are two parts to a spectrum. You have the continuum, and you have the spectral features. I'm going to be referring to these terms a lot, so that's why I got this slide in here to show you exactly what I mean. So the continuum, you can see the laser pointer, is that curve that has been drawn out up here. It's just an illustrative curve. That's describing how bright the different areas of the spectrum are. This is a historical sketch of the spectrum of the sun, and it's showing that the sun is brightest at the yellow wavelengths, right? Where we draw the sun as yellow. Sun's not very bright when it comes to purple wavelengths, right? Sun's not purple. So the continuum is faint. So that's all that we're talking about. When I say the continuum, that's all I mean is just the brightness, the general shape of the spectrum, right? And then there are the spectral features. Those are small, those are narrow, those are things like the lines that are coming from atoms in the star's atmosphere, right? So that's the difference between the continuum and the spectral features. There are lines and there are molecular bands. You'll see examples of both of those shortly. All right. So our modern spectral classification system is the way that we sort out all the different types of spectra that we see when we look up at the night sky through a diffraction grating. It was invented by these lovely ladies here who worked at the Harvard College Observatory back around the beginning of the 20th century. Annie Jump Cannon is in this picture. I cannot point her out to you, sorry. But she was mostly responsible for creating the Modern Systems Spectral Classification, which you may have heard of as a OBAFGKM, or the Morgan Keenan, or the Harvard Spectral System. Those are all different names for the same sort of thing that we're using today. She did this, and the other ladies at the Harvard College Observatory did this, by looking at images like this one. So this right here is a print made from a glass plate, because that's how they took their images back then, with glass photographs instead of digital. And they put a prism on the front of the telescope so that they got a whole bunch of spectra, just like the one I showed you at the beginning, one for each star. And there are some small differences. And this is what they were trying to figure out, what are the differences? Are there different patterns that show up, predictably? What do they mean? That was the purpose of creating the spectral classification system. So this plate here was actually annotated by Annie Jump Cannon herself. So the writing is on it. She pointed out up near the very top is a class M star. There's a class Q below that. Class Q did not survive to the modern day. Don't go looking for Q stars, they're not out there. But after much refinement, they took these spectral types that they got from the plates, and they created a system which looks like this. So these are the final spectral types that they sorted them into. And I'm showing it without labels first, so that we can just focus on how they did that sorting. So what they did here was they took the spectra and tried to look for recognizable features that showed up in every spectrum, and then sort them by strength, right? So let's go ahead and put some labels on there. Oh yeah, there's the spectral types, and then here we go. So here are some of the spectral features labeled. So like, for example, if you have a star, it's got lots of sodium, and it doesn't have any helium in it, doesn't have any hydrogen in it, you would put it down near the bottom of this diagram, right? Because you see that there's a line that shows up at the same wavelength as we see sodium lines show up when we test them here on Earth. If you have a star and it's got lots of helium in it and a little bit of hydrogen, you put it up at the top with the stars with lots of helium and a little bit of hydrogen. And when you sort them like this, in this one particular sorting, you can get a smooth gradient through the spectral types. So you can see pretty clearly here how the changes are gradual. There's not really any huge jumps on the trip from top to bottom on this diagram, right? So that's how we got the modern order. Yes, do you have a question? That's a good question. Okay, so the question, I'm going to repeat it for the people who are watching online. The question was, I remember the spectral types by the mnemonic, "Oh, be a fine girl, kiss me now." That includes an N at the end of it. Where did the N go? Spectral type N used to be a rare spectral class. It has been dropped since and kind of bundled into the carbon star spectral types. So carbon stars have a few different kinds of subdivisions now, and one of them is what used to be called spectral class N. So, and that was a relatively recent change. So that's probably what you're remembering, is that carbon star designation. So good question. All right, so that's this logical sorting here of the gradient of the different atoms, showing up in different spectral types. That's why the alphabet is all out of order on this. It would be much more convenient for us if they were spectral types A, B, C, D, E, F, G. They are not. They are O, B, A, F, G, K, M, because when the lovely ladies at the Harvard College Observatory were first doing this, they assigned the letters according to groups, which turned out to not really be real. So when we settled on the final order of things, the one which we were able to link back to physics and the way that the stars actually work, the letters got scrambled, and we have to deal with that for the rest of time, probably. That's correct. In fact, let me go ahead and show you guys that. So that is the logical order, is by temperature. And so basically, that's what you're looking at when you see this gradient. If you can identify a star's spectral class, you can match it up to one of these types, O, B, A, F, G, K, M, then you have a rough measurement of its temperature. There's just some atoms that like certain temperatures better when it comes to grabbing light out of the spectrum. So there's one other fact about a star, which you can derive by looking at its spectrum at low resolution. And that is shown in this example here. Now, this one is a lot more subtle. These are two spectra that I took using my telescope. One of them is of the star Vega, that's the one on the top. And then right below it, there's no border, but you'll see the lines get a lot thinner on the bottom half of this image. That's because that's a spectrum of the star Deneb. Now, Vega and Deneb, when you rate them on the Harvard Spectral Type Classification Scheme, they come out exactly the same, okay? They are both A-type stars of like exactly the same subclass even. I mean, they're very, very close to each other. But when you look at them, there's actually a pretty big difference because Vega, it's got these huge fuzzy dark lines, right? And then Deneb has these really dainty thin lines, and you can see some extra lines in between. It's not the same spectrum. So the difference here is the luminosity. So stars which are bigger and more luminous tend to have skinnier lines, fainter lines. Using these two facts, the one that you can sort out different spectral types and thereby know a star's temperature, you can also look at how skinny the lines are and thereby know a star's luminosity or how bright it is. That gives us a way to create what we call an HR diagram, Hertzsprung-Russell diagram. You plot the temperature on the x-axis, left to right, and you plot the brightness on the y-axis, top to bottom. So when you do this for a huge amount of stars in the sky, in this case I use the Gaia data set, if any of you guys are familiar with that. It's a space telescope up there that's been taking data on a truly stupendous number of stars. When you do this, you wind up with this diagram, HR diagram. It's got a very characteristic shape. Let me go ahead and highlight. Oh yeah, so there's the there's where the spectral types fall on the diagram, by the way, mapping to temperature. So anything below the M there, that's an M-type star. Anything below the K is an M-type star, so on. So this stripe right down the middle, where almost all of the stars go, we called that the main sequence. So if you're like me, then in learning about the HR diagram, you may be going, why is there a main sequence? What does that? What makes all the stars group together? There is a explanation for that, which I find very satisfying, even though it took me 7 years to find out the answer why. Now I know it's intuitive. I'm going to try and share that explanation with you. So here's the explanation. It's called hydrostatic equilibrium. Basically, when you take a chunk of hydrogen and you let it collapse under its own gravity, which is what a star is, it's a collapsed cloud of hydrogen, then the pressure in the core is going to rise, and eventually it's going to start fusing hydrogen into helium, right? That's a star. It's producing energy. The energy is going to push on the material in the star as it tries to escape the star, right? So the light escaping the star is literally exerting a force from the inside of the core. All right, that's fair. But why does that relate to the main sequence? Well, for a big glob of hydrogen, like a star, you know what the material is, you know what the size of the star will be when it hits the critical density where it starts fusing, and you also know when it's going to reach a balance, and that's because in hydrostatic equilibrium, if the star were to contract anymore, that would power up the fusion. The fusion increasing would cause more light to stream out of the core, which would blow the outer layers of the star a little bit farther apart, which would power down the fusion, and so it would return to its previous state. That's what's happening in all of these stars, is they're at this perfect balance point, where wherever they started, this is where they converge to, because if they are out of balance, they just naturally return to this state. So that's where we get the main sequence from. Now, if you're like me, and that makes sense to you, then you're probably asking, where did the other stars on this diagram come from? Those are the fun ones, the ones that are not behaving in the way that you can predict with just a couple equations in hydrostatic equilibrium, right? So those stars, the fundamental difference there is that we can't assume that they are just blobs of hydrogen, like you can on the main sequence. The main sequence one are blobs of hydrogen burning hydrogen into helium, and that's it. But when a star runs out of hydrogen, it starts to do some really interesting things. Okay, you've got other elements that start to be created other than helium. You've got weird contractions and expansions that go on, and all of that throws the star out of balance. It might find a new hydrostatic equilibrium somewhere else, or it might go through a transition, moving across the HR diagram. Lots of interesting stuff happens then. That's what I'm going to focus on. The rest of this talk is showing you guys just what sort of exotic stuff these evolved stars do. So before I get into that, there's a kind of a dividing line that astronomers like to draw on the HR diagram, and that's the line between high mass and low mass stars. We tend to put the dividing line at somewhere around 8 times the mass of the sun. Now, a star that's 7 times the mass of the sun might sound like a huge star, and it is, but it's going to behave pretty similarly to the sun, so it kind of makes sense to group it into the sun-like stars. But once you get to about 8 times the mass of the sun, then the stars start behaving totally different. So that dividing line is probably right about there, and it makes the difference between whether a star is going to end its life in a very peaceful way, transform into a planetary nebula that we can go out and look at in our telescopes, or whether it's going to blow up in a supernova violently and sterilize the nearby planets, right? So that dividing line is right about 8 solar masses. Let's take a look first at the sun-like stars, what happens to them. So I think this is gonna pull up, yeah, this is gonna pull up one of our videos. So
I have to break.
Go ahead and pull up the one. I think file name's kind of cryptic, but it's like 1TAMS or something like that.
1M sun.
Yeah, that, sure.
Got it.
All right. So this video is starting out with just showing you in pink. So this is a simulated trail. Oops. Put that up there. All right. So yes, we're gonna play that again in just a second. So this is showing a simulation of what a star, just like the sun, does when it dies. Actually, all throughout its life. It's drawing a pink trail on the HR diagram to show you where it goes to.
I'm fixing it. Hold on.
Okay, take your time.
Yeah.
So this first pink trail here, that's just showing how the star got to the main sequence. And in the main sequence itself, when it's burning hydrogen, I mean, stars have so much hydrogen, that phase lasts effectively forever, right? You know, the sun has got like another 4 billion years on it, right? And when it dies, I mean, if I played this video back fast enough that you guys could get through the main sequence without, you know, perishing with boredom, then everything else would go by in a single frame. So we're gonna just skip over the main sequence. And now, the star is now beginning its death. Now watch that. All right, so we're gonna go back over that in detail. If you could play that one more time, I would appreciate it.
Yep.
So when the star begins to die, runs out of hydrogen, it starts fusing hydrogen in a shell around its core. This is just like the last dregs. You know, it hasn't got anything left in the core fusion area, but it can get by a little bit. So it goes up the red giant branch. That's what it's doing right now. Comes back down for a minute. I'm gonna highlight where, see that blob of stars right there? So that right there is called the red clump. That's the point where a star goes back into hydrostatic equilibrium, but not burning hydrogen, burning helium. So it gets to a point where it's collapsed so much that it can burn helium, and then, okay, it's happy in that hydrostatic equilibrium there for a little bit. And then once it runs out of helium, it starts burning the last dregs of its helium. You know, it's out of usable helium in the core, but it starts burning just the last bits that it's got outside the core. That powers it up the asymptotic giant branch. And I'll go to the next slide now and show you guys a clearer picture of that asymptotic giant branch.
You have control again.
Okay. There we go. Okay. So, here's the sequence. Star is on the main sequence. It's happy. It's burning hydrogen. It runs out of hydrogen in its core. It tries to get by on what little bit it's got left outside the core. That powers it up the red giant branch. What moving up the red giant branch literally means on this diagram is that the star is getting brighter. That's what's making it move up. And it's getting colder. That's what's making it move to the right. So that's happening because the outer layers of the star are expanding. The balance has shifted. Then it gets to the point where the inside of the core, the pressure is high enough that it can fuse helium, so it very suddenly drops down, and it hangs out in the red clump with the happy helium fusing stars for kind of a while. And then it runs out of helium in the core, tries to do the same thing it did on the red giant branch, only with helium, burns just the last bits that were left outside the core. That powers it up the asymptotic giant branch, which for years I thought that this was like this super cryptic thing because it's got asymptotic in the name, and that's like a really obscure word. No, asymptotic as in approaches. So they really just mean this is giant branch addition to, it approaches the original giant branch. That's all that means. It's no big secret. I only found that out like 2 months ago when I was preparing this talk, that there's nothing special about that. So, and then when it finally runs out of the last dregs of its helium, the star completely destabilizes, okay? So this is now, at this point, it's a dead star, and it starts going through these wild pulsations, and the outer layers of the star basically just float off into space. That creates a planetary nebula. Meanwhile, the part that we would still call a star, well, the outer layers are leaving it, so basically all that we've got is a core. Right? So as the outer layers leave it and more of the core is exposed, as the outer layers are leaving it, then we see the very, very, very hot core. And so it shoots straight left on the HR diagram because it's getting hotter and hotter and hotter. And it's going to go, I cut it off on this diagram because there's no way I could include it, but the core is like millions of degrees. So it's way, way, way out the building, right? And then eventually the core will cool down. It's going to lose its heat to space because it's not making any more energy. And it will come back in the form of a white dwarf star. So it'll just slowly fade and get colder and follow this track of very faint white dwarf stars down to the bottom of the HR diagram. That right there is the future of the sun in 4 billion years, give or take. All right, so let's go ahead and take a look at what some of these evolved low mass stars actually look like now that you've seen the whole scientific diagram explanation. So this right here, I think you might have to pull up the video for this one too.
Okay.
And honestly, I don't remember. I think the file is really cryptic on this.
Yep, I see it.
Okay, great. There we go. Okay, so this right here is a magnetohydrodynamic simulation of an asymptotic giant branch star. Fancy way of saying this is the most photorealistic simulation that scientists have right now of what it would look like if you were on a planet around one of these stars and you looked at it in like a solar telescope. Okay, that's what you'd see. These stars are not like what most people think of stars as being. Their surfaces are effectively boiling and they're just losing material in all directions. They're not quite destabilized to the point of being planetary nebulae yet, but boy, they're getting there. We think that the material coming off of these stars, just kind of gradually fuzzing off into space, may be responsible for a lot of the heavy elements which are out there in the universe, which help to create planets like Earth. All right. go ahead and take a look at the next slide, please. Okay,
Back
so let's look at some examples of asymptotic giant, or evolved solar-like stars. So here are 3 famous examples. Arcturus is a star that used to be quite like the sun. Now it's beginning its first climb up the red giant branch. You can see that just by its location on the HR diagram. It's on the kind of the bottom side of this branch, which is trailing off towards the top, and it's about halfway up. So we don't have it at the top yet. So what it being in that location on the HR diagram tells us is that Arcturus has run out of hydrogen in its core. It's now just kind of trying to get by on the last dregs of hydrogen in the shell outside the core. During that shell burning, that'll power it for a while. It'll continue to get colder. In, I don't know, 100,000 years, Arcturus is probably going to be a star much brighter than Betelgeuse and much cooler, and we'll have this like super bright red star in our sky, very, very red. Not quite there yet though. Capella is a star which has actually already been there. It's a multiple star system, but they're pretty similar, the stars that are in it. They have already gone up the red giant branch, got into the point where the core was dense enough that it could start fusing helium and drop back down to hang out with the stars over here in the red clump. So that's what Capella is doing. It's pretty happy for the time being. It's going to be there a while longer and keep using up the helium in its core. And then we have a star. This one's a little more obscure. It's not visible to the naked eye, but it's a really beautiful star if you ever get the chance to check it out. T Lyra. Actually, has anyone here ever seen that in their telescope? T Lyra. Yeah, right? Okay, great. It's a really cool carbon star. So very, very, very deep red color. And the red color in this case comes from both the temperature and the spectrum. Let me go ahead and show you the spectrum of this. All right, so let's go around in the same order that I introduced these stars. Arcturus here, since it hasn't made it all the way to the right side of the red giant branch, it's kind of a medium temperature red giant. And so we see all of these very, very spiky lines from different metals like magnesium. That's this huge one here. But it's not overwhelmingly red. When you look at it in the sky, it's more just like an orange. And that's because the continuum is not super cold. It's only like a medium temperature. Capella has a spectrum actually quite similar to the sun, because the sun is straight below it here. So the only difference is the luminosity, right? The overall spectral type is the same. So we see a lot of spectral features that we see in the sun. There's hydrogen, there's calcium, there's some of that magnesium too, sodium, all sorts of Fraunhofer lines, if you're familiar with those. And the continuum is centered on the visible region, the green and the yellow, just like the sun is. And then T Lyra, fun one. So this star is very cold, so its continuum is radiating most of the light off the right edge of the diagram in the infrared region. Most of the energy is actually coming off of wavelengths that we can't see. What is coming off of the visual is incredibly darkened by these carbon spectral features. So molecules, they make these very wide chunks out of the spectrum instead of narrow lines. That's what we're getting here with carbon molecules. So this star, it actually is cold enough that instead of blowing molecules to smithereens before they even really get a chance to properly form, it's built up quite a large quantity of these carbon molecules, C2. And so that makes the problem of this star not having much blue light much worse. It absorbs basically everything that's left, and then you just see an extraordinarily red star. Look at your telescope. Okay, now here's one. Oh, that's a good question. Okay, so we had the question, where would Betelgeuse be? Actually, you know what? I'm going to get you to hold that thought, because I have Betelgeuse coming up in a couple slides. All right, but before we get to Betelgeuse, here's just one example that I couldn't resist sneaking in because I took this particular spectrum and I think it's super awesome. This is a star like what Arcturus is going to turn into when it reaches the tip of the red giant branch. So it's only about halfway up right now, but once it gets over to the right side and it hits the very cold temperatures of T Lyra, it's not yet, at least, going to have the same carbon abundances that T Lyra does, but it will have titanium oxide molecules. Now, those are the first molecules that we see show up in these really cold stars. And they do this beautiful sawtooth pattern across the entire visible spectrum. And when you look at this in a telescope visually, just looking through a diffraction grating at the spectrum, oh, it's gorgeous, let me tell you. You can see it in Betelgeuse if you ever want to look at that for a diffraction grating. All right. Okay, so we just got a question. Did I add the red lines or are those real? So basically what you're seeing here is most of this frame is a graph version of the spectrum. And then on the bottom is the photo version of the spectrum. So this is going back to the beginning of the talk when I showed you the different ways that you can represent spectral data. So the bottom along here, that's the photograph that I took with my telescope. And then the red line and the gray line are two different scientific graphs made from the photo. Sure, okay, so I just got another question, which was whether I can explain what a diffraction grating is and what the equipment that I use to take these spectra looks like. This is something I'm happy to talk about in more detail after the presentation if anyone wants to come up to see pictures, because I haven't got any pictures of that in this slide deck. But basically, the diffraction grating is a piece of glass with some very fine grooves etched into it, like microprisms. And my particular diffraction grating is one of the really common ones that are sold to amateur astronomers. It's in a little filter housing, just like a moon filter. And you can screw it onto an eyepiece or a camera, just like you can with a moon filter. And when you look through it, it has the same effect as a prism because of all the little microprisms. And you get to see the spectrum off to the side of the star. So that's what this photograph is. When I took this photograph, the star itself was way over here to the left, right about there, and I cropped it so that you could see the spectrum better. But when you look through a telescope, you see both the star and the spectrum off to the side. And again, I can, if you're curious about the process, I have some pictures on my phone that I can show anyone who's interested after the talk. Okay, so that's our tour of the evolution of sunlight stars. I also want to go quickly through the evolution of the not sunlight stars, the massive stars, because frankly, my heart belongs to them. They are the coolest stars in the sky, even though they are the massive stars that does not get to hold the title of the coldest stars in the sky, but some of them are pretty cool anyway. All right, so here we are back at our friendly HR diagram. So remember, the dividing line is up there to the left of the red clump, somewhere around here is where you have the dividing line between stars which are massive enough to go supernova, which are the ones we're about to take a look at, and stars which aren't, which are the ones we just did look at. So I'm going to go ahead and play a video. If you could bring up the
I got
video.
you.
Great, thanks. So we're going to look at a video that's just like the one that we did for the sunlight stars. All right, so this here is showing, first of all, how the star got to the main sequence. We're going to do the same thing. You know, it spends so long hanging out on the main sequence, we're going to just skip over that part. And all right, here we go. So the star right now, just pointed out, is over on the left edge of this track. And it's a hot blue bright star, and then it leaves the main sequence. It spends like no time at all in the yellow supergiant phase, becomes a red supergiant, might go through what we call a blue loop. It's doing one now, becomes a blue supergiant for a little bit, back to red, gets bigger, and simulation stops here because that star just went supernova. Unfortunately, I didn't program in a supernova graphic or anything like that, but simulation ends there. So if we could play that back one more time. Thank you. All right, so this time watch carefully for the yellow supergiant phase. That's when it very suddenly dashes over towards the right. Polaris, by the way, is currently in the yellow supergiant phase. It's a very, very, very rare phase, and it's a weird coincidence that the pole star is in that phase. All right, now this star is going back. It's actually becoming a yellow supergiant again, not making it all the way to the blue. Some of them make it all the way to the blue, some of them don't. But and then it ends its life as a supernova. So if you go back to the slides now, I can show you guys that in a more controlled fashion here. So, there we go. Okay. All right. So massive stars, they do the same thing that low mass stars do by starting on the main sequence, burning hydrogen, and then running out of hydrogen. The difference here, and what ultimately winds up making them go supernova, is that they don't have to, struggle to burn helium and then fail to burn anything else. They have got enough mass and enough pressure in their cores that they can just ignite helium, and then once they run out of helium, they can ignite carbon. They can keep going. They can keep burning more fuels. Now, depending on how massive it is, you might get even more fuels that are available for the star to burn. And these start burning in shells around the core and powering the star to grow the same way that the red giant branch stars, when they started burning stuff in shells, then they tended to expand. Same thing happens with these high mass stars. They tend to expand, and as they do so, they become red supergiants. Now you saw how huge the dot got in the video. That was trying to scale it appropriately, so that you had a tiny star on the main sequence becomes a huge red supergiant. Those are the largest stars that we know of in the universe, are the red supergiants. And yeah, this blue loop thing that I've included here, a lot of massive stars do it, and we have no idea why yet. Like, if you manage to figure it out, you better publish, because that's an open question, is why would a red supergiant just suddenly turn yellow or blue and then go back to being red? Like, that doesn't make sense with current theories, but so it is. We have observed that this happens. It happens in our simulations, and there's stars up in the right region, the HR diagram for that to happen. So yeah, maybe you'll hear about it in the news someday when someone finally figures it out. It's possible for a star to go supernova while it's still on its blue loop, but most of them probably come back over and hang out as a red supergiant a while longer before they eventually go supernova. The supernova happens when they run out of fusible elements. No matter how massive the star is, once it gets to iron, it's going to run out of fusible elements. Iron is an energy sink, and it's going to build up a bunch of unfusible iron in its core. It takes more energy to fuse iron than you get out of it, which is the problem with it. So you can't transition to any fuels above iron because it's blocking the way. So the core fills up with iron, and then the star kind of can't do anything more. It destabilizes, but unlike the very gentle destabilization that happened with the solar mass stars, the giant stars, the 8 solar mass and above stars, they blow up all at once. You don't get the smooth fade into a planetary nebula, you get a catastrophic explosion. It's supernova. All right, so that's the evolution. Now let's go into the fun bit, which is, what does this look like? So you can go ahead and pull up this video. I've got a magnetohydrodynamic simulation of these red supergiants as well. This is what the largest star in the universe probably looks like. As soon as it comes up. Okay, that's a little trippy. Okay, there we go. All right, so these stars, just like the asymptotic giant branch stars, their surfaces are boiling, these large convection cells, which are coming to the surface and kind of bubbling over, that happens on a time scale of months. And we can see that here on the ground, well, in multiple ways. Some of these stars are large enough that we actually can see their surfaces. Not in quite this level of detail, but pretty dang close. You can do that with interferometric arrays. In fact, I think even Hubble was able to resolve Betelgeuse's surface just slightly to check on it after the Great Dimming event. And you can also see these great bubbling over in the variations of the brightness of the star. So sometimes you've got these big, bright, hot upwellings that come from near the center of the star. They reach the surface, and then you see the star get brighter here on Earth. Other times, the atmosphere kind of fills with ash as the colder parts reach the surface, and then we see the star get fainter. So that's another way that we can see this kind of activity. All right, so now let's go take a look at, go back to the slides.
You're there.
Cool. There we go. All right, so here are two examples of these high mass stars. Here's Betelgeuse. We're finally getting to it. So we've got Spica, which is a main sequence massive star. Okay, so it's still burning hydrogen. It's happy. It's healthy. It's going to live for a while longer. And then we've got Betelgeuse, which is the one that's going to die any minute now, right? I mean, like tomorrow, it could go, wait, no, not tomorrow, it's behind the sun right now. In a couple months, it could go supernova, and then we'd all have a celestial fireworks show. I'm crossing my fingers. All right, so Betelgeuse has run out of hydrogen in its core, and it's switched over to burning something else. But we don't know what it's burning in its core right now. And that is the factor that tells us whether it's going to go supernova tomorrow or in 100,000 years. You know, we just don't know which stage is it at. We haven't figured out how do we look inside this star? How do we figure out which fuel it's on? We get a countdown. We can look at the outside of the star at least and take a look at its spectrum. So let me go ahead and pull that up. So you can see that there's quite a diversity in the spectra of these massive stars, and they get even wilder than this. I'll show you an example in a second. So Spica is an incredibly hot star. It can get much, much, much hotter than the solar type stars get. Massive stars in general, they tend to be very hot. So basically, most of its energy, kind of like how T Lyra, most of its energy was coming off in the infrared. Well, Spica, most of its energy is coming off in the ultraviolet. So we see it sloping up towards the left of its spectrum. The blue region is really bright, and then the ultraviolet, if you could see it on this diagram, is way even brighter. It's got a lot of hydrogen lines because hydrogen lines like to show up at high temperature. It's even got some helium lines in there. Helium tends to show up only at very, very high temperatures. So that's why we place it on the HR diagram as a class B star, one of the hottest. And then Betelgeuse is way on the other side, on the cold side of the HR diagram. It's a class M star. That's the coldest star that we ever see in practice. There technically exist colder stars, but like we haven't been able to see them until like the 2010s because they're so faint and so cold, so hardly even counts. So Betelgeuse up here, it's got the beginnings of those molecular bands I was talking about that happen when stars get cold enough. It's also got a bunch of metals in there. So you can see both the titanium oxide chomp sticking out of the spectrum and some of the lines, like I pointed out earlier, there was a magnesium. So there's actually some of that magnesium showing through in Betelgeuse's spectrum too. It's got some of the sodium too. Those lines that we look for in the cold low mass stars, they're also showing up here in Betelgeuse's spectrum. And then we go ahead and take a look at my next example. Oh yeah, I forgot I put this slide in here. I just had to show it again. I showed you guys the spectrum at the beginning, but come on, I'm proud of it. So this is Betelgeuse's spectrum in all its glory, and this is what you would see if you looked at Betelgeuse through a solar spectroscope and you were on a planet, like orbiting around Betelgeuse. So this is the up close and personal view. When you look at it in a telescope, it's almost this cool. It's just not this tall because Betelgeuse is so far away. You know, it's only going to look like a speck in the telescope, and so the spectrum looks like a narrow line. instead of something tall. But I think when you do a long exposure like this and let it stretch out to be super tall with a star trail, I think it looks cooler that way. Alrighty, so closing on the last example here. This is one of those really exotic high mass stars, P Cygni. Now, this one is near and dear to my heart. It's a weird star. We call it a luminous blue variable. So luminous blue variables are extremely unpredictable. Eta Carina, if any of you guys have heard of Eta Carina, it's a luminous blue variable. It's currently sitting at, I think, like 7th magnitude down in the southern hemisphere. It was briefly the brightest star in the sky back in the 1800s. No one saw it coming. No one knows when it's going to do something like that again. The same thing goes for P Cygni. P Cygni could just up and decide to become the brightest star in the sky if it wants to, and it might do that. And we should all be keeping an eye on it, I think. So what happens with these luminous blue variables is they are evolved stars that have they've started out as high mass stars on the main sequence. They've gone over, they've become red supergiants probably, and then they do their blue loop thing and they come back over to the blue and they reach a region of the diagram where the hydrostatic equilibrium, yeah, okay, you can call it hydrostatic equilibrium, I guess, but it's pretty unstable. The star's pulsating, it's kind of shivering, its outer layers are tenuous, and sometimes it's losing mass because of these pulses grow too strong and parts of the star tear off and fly off into space. And every now and then, this gets taken to an extreme in what we call a luminous blue variable event. No one knows what causes them yet. I'm trying to figure it out myself. This kind of star, which has been showing a relatively normal spectrum, I'm going to call it normal, even though it's different than all the ones we've seen before, suddenly becomes maybe 3, 4, 5 magnitudes brighter and turns into a yellow supergiant for no reason at all. We haven't figured out why that happens, but it does. And P Cygni could do it tomorrow, and then we'd have a brand new bright yellow star in the middle of Cygnus. So cross your fingers. You can see here in P Cygni that it actually has bright lines instead of dark lines. Another thing I like about this one, those lines are coming from the material, which is streaming away from the star because it's unstable, because it's got this really dense wind. It's pushing out all this hydrogen and helium, and it's lighting it up like a fluorescent bulb on its way away from the star. And so you get fluorescent bulb lines of hydrogen and helium, which, here we go. Yeah, so that's what that is. That's hydrogen right there. That's helium. That's hydrogen. That's helium. And that star's just decided to do that, I guess. It's just going to become giant space fluorescent bulb. Why not? Alrighty. So, in conclusion, that's an HR diagram. Those are spectra. And both of those things are really super cool. I hope I've convinced you. Any questions?
Yeah.
Okay,
I
you
do.
have a question?
Well, this to be kind of on the fringe of your talk, but as these stars go through these cycles, they're changing temperature, mass, and density. Does that affect the speed of its rotation? And also, if it does, if there were any planetary systems near the star, would it affect those planets by a change in the rotational rate?
Okay, that's an interesting question. So I'm going to repeat it for the people online and also to make sure I got all of that. So the question was, as these stars go through these changes, that change the temperature, the density, all of that stuff, does that change the rotation rate of the star? And if it does change the rotation rate of the star, does that affect the planets? Did I get that right?
Yeah.
Okay, so the answer to that is, I don't know. I know that stars' rotation rates change with age. I don't know whether that's tied to the actual like the changes in the size and the temperature, or if it's related to something else, you know, the mass leaving the system or something like that. All I can tell you is that the rotation does change with the age of the star. We use that as one of the signals to measure how old a star is. As for about the planets, again, I'm not an expert on that. However, I just actually heard in one of the MIT exoplanet group meetings the other day that there are some people who have been doing research into how rotation affects like planets' occurrence rates, and also how these stars, you know, when they swell up, chances are a lot of these, like the red supergiants and especially the asymptotic giant branch stars, when they go through these stages that puff them up, they're probably going to wind up eating some of their planets if they had planets around them. And people have been studying actually what happens to those planets, you know, how close to a star is too close, and what happens if one like enters the very upper layers of one of those really puffy asymptotic giant branch stars. How long will it survive? Will it keep orbiting inside the very top layers of the star for a while, or will it just immediately crash into the core? You know, that's an active topic of research, and that's about all I know about that. So,
Thank you.
any other questions?
Could you explain the vertical axis again on the HR diagram? That's mass, but I don't understand the number going from.
Oh, sure. Yeah, I probably should have done a better job of that earlier. So, the vertical axis here on the HR diagram is brightness. That's really what it reduces down to. Here I have it labeled as absolute magnitude because that's the proxy for brightness that I use. So basically that's saying the magnitude of the star if it was 10 parsecs away. So it's a way of comparing the actual brightness of the stars, not just the brightness as we see them from here on Earth. So if a star is brighter, it winds up towards the top. If a star is faint, it winds up towards the bottom.
I got confused when we were looking at the mass of the stars being high up there, and it doesn't really relate to that.
That's actually, it does kind of relate, and it's a good point. So massive stars tend to be brighter. They're the brightest stars in the universe, and the ones that we see the most easily as a consequence. We can't see stars like the sun very far away from the sun. We tend to see the massive stars because they're the ones that shine across thousands of light years of space. I'm currently studying one that's in the Large Magellanic Cloud. It's in a whole different galaxy, and yet, you know what magnitude it is? It's magnitude 10. You could see it in binoculars if you wanted. And if you were in the Southern Hemisphere, like I wish I was. Another question?
My understanding, luminosity of the stars is proportional to its area and also its temperature. And so it's the absolute magnitude that bring on that
That's a good question. So to repeat for the people online, it was about whether the absolute magnitude is to level out the playing field, so to speak, taking into account both a star's surface area and its temperature. Those were the two factors you mentioned, right? And luminosity. Okay, surface area, temperature, and luminosity. So not quite, at least in this case. What absolute magnitude is mapping most directly to is luminosity. The surface area is related in the sense, like you mentioned, more surface area means more luminosity, but it's not directly included in the calculation. Same thing for the temperature. Stars of a certain temperature tend to look brighter to us here on Earth because when it's a certain temperature, it puts off most of its light in the visible region. But that is not actually included in the calculation. The calculation is just look at how bright a star looks from here on Earth, look at how far away it is, and then do the necessary math to figure out how bright would it look if it was 10 parsecs distant instead of whatever its distance is. And that's all of the math that's behind the absolute magnitude thing. Yes?
And one other thing, I don't know where one of those steps that the scale on it, we might discuss. When you take the anything outside the range, visible, you're looking at a little bit, but you're not necessarily just with the light that perspective going on.
Yes, okay, that's a really good point. So this one is more of a clarification than a question. So a lot of these spectra that I've shown, the visible region, the part that we can see with our eyes, is the middle part of the spectrum. But there's actually a little bit of ultraviolet and infrared included on the ends. So just fun fact for you there. You can do that because cameras, like the typical astronomy, astrophotography cameras, they do tend to be sensitive to ultraviolet and infrared light. So you have that option of studying those regions if you ever want to do spectroscopy like me.
Somebody asked the numbers on the absolute magnitude scale. It's logarithmic. So in our system, it's about 2.5 times brighter for each number. 2.5 times dimmer going down, brighter going up. So 5 magnitudes is 100 times brighter or dimmer. And then you keep going.
Yep, absolutely.
Somebody asked about the temperature, it's T to the 4th power, so you double the temperature, you have to raise that to the 4th power. It's that much brighter. It's like turning your dimmer switch up. Dimmer switches
Yeah, interesting, thank you. So just to repeat for the people online, we were just talking about what the axes represent here, really, the temperature and the brightness axes. So the brightness axis is logarithmic, just like, I mean, it's the same magnitude scale that we use when talking about the brightness of stars as seen from Earth. It's just we've compensated for distance, basically. So each step in magnitude, going from a magnitude 5 to a magnitude 4 means a 2.5 times increase in brightness. So thank you for that comment. Any other questions? All right, thank you for your time.
minutes, hours, seconds, what?
Well, it was about 90 seconds, so yeah.
90 seconds.
Do I get the second?
Very, very nicely done. Thank you, Lauren. I'm sure people will have questions about how you got those spectra. That's great. So we have our Eclipse glasses sets if you'd like to have them. They're $5 a piece. We have our volunteer list for people to come and help with our convention. There's the list, thank you. So there's lots of things to do. Anybody else out there? Mike? Oh, Don, you want to come give a report on the dome? You don't have a choice.
12.5% of our membership come to these
I'm not the one really to give a final report, but I have heard from people who are working on it, and for those of you who know what's going on, we've developed a system for rotating the dome. If you've ever been out to the dome, you know they get stuck routinely, and lately it's been stuck almost totally. But we put metal gear system down here inside of the circumference of the dome with a drive gear that is driven by a motor, and that we've gone through several iterations of getting it to work. Anyway, long story short, by the end of this week,
That's what they do.
I understand that it's going to be working,
But
and all we
it is
have
what
to
it
do
is.
is get a little fancier switch so that we can put a switch next to the telescope, and
It is what it
whoever
is.
is running the telescope often me. can move the dome from a switch that's close to the telescope. And the other project, these are two projects that have basically been driven by the convention. So we wanted to have it all done by the time the convention comes around. The other project, which I think was completed Wednesday, but I'm not sure, is a railing, handrail up the staircase. If you've been up the dome, you know we needed one, and now we have one.
So we have our guest night on the 12th, and we have our members night on the week after that, the 19th. So those of you who come to either one of those, kind of look around, things that need to be kind of cleaned up in the observatory. We had a good work day, but there's still some things that could be improved, I'm sure. And we had a great time cleaning out the brush last month. So anything you see that can make it more guest friendly would certainly be welcome. We've got a couple of scopes out there we need to take out and be sure their finder scopes are lined up and some of those things that'll need to be done. So anybody else got other questions? I apologize for sitting down. I had surgery a couple of months ago, and standing up sometimes is not the best for me. All right. So anybody going to go to Louis for lunch? Or after lunch, whatever time that is.
I hope all the best to you.
Is anybody there? Hello.
Hello, Richard.
Yeah, hi. I was speaking, I guess that was John that was speaking there, and he was sitting down, I guess, but I couldn't see him.
Yep, correct.
So the lights that are back there on the behind the speakers are so bright that it's hard to see anybody. You there? Now I can see what's going on.
Okay.
Just some suggestions, though.
No, I got you. Yeah, I don't like when those lights are on either.
And maybe if your camera could be a little bit closer to the front where we could see the speakers.
Yeah, that one's gonna be tough because it's hard to get that connected to my computer, but we've been working on other ways. We'll keep working on it.
Okay, well, this is my first time to join you. I just thought I'd throw those suggestions out there. We use Zoom for the Amateur Radio Club here in Ponca City.
All
And
right. Well, appreciate. Yeah, I agree with all those notes. I would love to move the camera forward. I'd love to get rid of those backlights whenever I can.
well, I understand that there's some restrictions on what you can do.
Yeah, I just need longer wires and then it becomes a tripping hazard. So yeah, it's just things we're working on. I do appreciate the notes.
Okay, well, I hope you all send me a Zoom invitation for some future events. Driving to Tulsa is not my best thing right now.
Understood. Yeah, I'll make sure John continues this and we'll make it better.
Okay. Well, thank you.
Thank you. Have a good evening.
You too.